Welcome back, everybody. Last lecture, I taught you the basics of decision trees. I gave you a simple decision tree algorithm, which is very commonly in use. But today, what I want to start by doing is describing some variations on the theme. Decision trees can be changed in many different ways. You can probably imagine 100 different ways to change them, and many of those ways will work under certain circumstances, depending on your application. So let me discuss a few of the ways that you can change up decision trees. I want to start by just briefly mentioning that you could use multivariate splits. Rather than just splitting on one feature at each internal node of the tree, you could take a non-axis aligned split, which means you have to look at more than one feature. How are you going to find those splits that are not axis aligned but might be good splits? Well, you can use other other classification algorithms that we have studied this semester, like a support vector machine. And also at the end of this lecture, I'll briefly mention another possibility, which is sometimes if you generate a bunch of them randomly and try them all out and see which one gives you the best split, that can give you pretty interesting results too, as we'll see later. But for now, let's look at linear but not axis-aligned splits as one way of changing up your decision tree. And so here is a example of comparing two different point sets which naturally are begging for a linear split, but one that's not axis aligned. And so if you just use the standard decision tree, like up top, to classify these points, well, you get a pretty big tree because you have to do a lot of cutting here to separate the red points from the black points. Whereas we notice that they actually are linearly separable in this case. And so if you have a decision tree that looks at both features at the same time, that could be a win. And so you could find that bottom split, again, with a support vector machine, with logistic regression, with linear discriminant analysis, or you could even use quadratic discriminant analysis if you want to get even fancier boundaries. One point I want to make here is that when you combine a decision tree with a linear classifier, you're now getting nonlinear decision boundaries, a nonlinear classifier. There'll be piecewise linear decision boundaries, but they won't be just linear anymore. And that gives you more flexibility if your data set even close to linearly separable. That might be a big win. So sometimes this may give you a better classifier. But there is a cost, well, sometimes several costs. One is worse interpretability. If the reason why you're using a decision tree is to get an interpretable result, you lose some interpretability. If you use all the features at each tree node, you lose a lot of interpretability. If you maybe limit yourself to 2 features or 3 features per node, then maybe not so much. The other thing that you lose, though, is speed. So decision tree classification is one of the fastest algorithms we've learned in a way because as you walk down the tree, to classify a point, you're only looking at one feature at each tree node. That makes it fast. If you do this, now you have to look at every feature, or at least a few of the features, at each tree node, and that slows it down. So for that reason, maybe we want to compromise. A compromise like at each tree node we can look at 2 features, or 3 features, but maybe not more than that. So that's one option, is that if you think multivariate splits will help, then maybe have multivariate splits on just 2 or 3 features per internal node. And so speed of decision trees while possibly benefiting from interactions between different features. And so you might ask, how do I decide which features I should use and which ones I should ignore? Well, probably the most natural way to do that is, if you have the time to build while you're building the tree, is to use forward stepwise selection to pick out 2 or 3 features that are going to be the best. Another thing you could do is you could just pick them randomly, and we'll talk about that later. Another thing you could do, which I don't know if this is done very often, but it's a thought, is you could run a lasso regression on your points and see what weights get set to 0. So before I move on from this topic, though, I want to clarify that although you can do this, it's not the common case. The vast majority of decision trees that you'll see used in practice are only looking at 1 feature per internal node. And for the purposes of the final exam, if we ask you a question about decision trees, about their complexity of the running time or anything else, you should always assume that we're only looking at 1 feature per node, unless we explicitly tell you on the exam that we're doing this. So please keep that in mind. This is a non-standard change, one that's sometimes fruitful, but only occasionally, and not the default. Any questions about multivariate splits? The next topic I want to briefly mention is regression. So, although decision trees are most commonly used for classification, you can do regression with them. And one thing that's a little odd about that is the most common way to use a decision tree for regression is a function that's piecewise constant. So not piecewise linear, piecewise constant, which means within any leaf node, the regression function has the same value everywhere in that leaf node. In your textbook, Introduction to Statistical Learning, gives an example of using a decision tree this way. And here's what they do. On the left, you can see a decision tree written as a tree. On the right, you see what that looks like in 2-dimensional space. So this is a tree on just 2 features. And so you can see that we have split up the space by doing these splits. And that splits it into 5 different rectangles. Within each one of those 5 rectangles, the regression function, our hypothesis h, is just a constant within each rectangle. And here is a 3D graph of the regression function you get. So you can see I'm not kidding when I say that it's flat within each region. Nevertheless, this can be a fine way of doing regression, of estimating what the value of f would be at nearby points. So when we do this, each leaf of the tree stores a label. The idea being that if we are searching on a test point through the tree and we reach this leaf, then we will return that label as our regression value. And the label is the mean of the labels of all of the training points that end up in that leaf node. which I'll call mu subscript s. Remember from last lecture that S is a set of indices of the training points that are in this particular node, tree node. And so mu of S is just the average of the labels of all the points that are in that index set. So when you're building a decision tree, we're going to do the same thing that we did for classification, where we try every possible split. We assign each split a score, and we choose the split that gives the best weighted average scores in the children. So we need a cost function, but the entropy cost function that I talked about last lecture, it's for classification. It makes sense when you have distinct classes and each point is either in class C or not in class C. But when you're doing regression, you need a different cost function. Entropy doesn't make sense for continuously valued labels. So now our cost function is really just going to be, well, one way to think about it is it's the sum of squared errors between each point's label and the label that we have assigned to the box. Another way to think about it is it's just the variance of all the labels of all of the training points in that box. So that's the variance of all the labels of all the training points in that leaf node. And if we spell it out as a formula, you can see it's just well, you can see it looks like a sum of squared errors. So one thing you'll notice that if all of the training points that wind up in the same leaf node all have the same label, then this cost is 0. But if their labels are not all identical, then the cost will be positive. And once again, the way we use this cost is when we're looking at all the different splits and deciding which split we're going to choose at each internal node of the tree, we choose the split that minimizes the weighted average of the costs, that is, the weighted average of the variances of the two children after the split. Any questions about that? That's all I have to say about decision tree regression. On to our third topic, which is when you are growing a decision tree, sometimes you might want to stop early. You know, the basic version of the decision tree algorithm that I taught you last Wednesday keeps subdividing tree nodes until every leaf is pure. We don't have to do that. Sometimes there are good reasons not to do that and stop subdividing tree nodes earlier before we reach purity. So why? Why would we want to stop early? There are many different reasons. One is you might want to just limit because if the tree is really deep, then it's slow to query points. If you want absolute maximum speed, then you want a tree that's not too deep. Maybe a better reason, though, is if you have a really huge data set, you might want to limit the size of the tree itself. Now, sometimes you have a small data set, and maybe you should build the whole tree, but there are problems nowadays where people work with literally billions of points. If you want to put 1 billion points into a decision tree and make all the leaves pure, you might wind up in a case where the size of the tree itself is close to 1 billion tree nodes, and that might be very unwieldy to process. So Also, if you have a billion data points, you probably don't need to refine the tree down to purity to get a good approximation. So in that case, you really don't want to build the whole billion node tree. You want to keep it smaller. An even better one is that when you refine a tree until it's pure, you might be overfitting the data a lot. Specifically, suppose that you have noisy data, meaning some of your points maybe just don't have the right label. They've been labeled incorrectly. Suppose, alternatively, that you have overlapping distributions. So maybe all of the points have the right label, but it's just the nature of the problem that you're looking at, that there's no clean separation between the people who default on their credit cards and the ones who don't. So, one distribution looks like this, one distribution looks like this. There's a zone in the middle where there's a lot of ambiguity. If you try to deal with that ambiguity by refining the tree until it's pure, you are definitely overfitting in that green region. So in these situations, refining the decision tree until the leaves are pure is downright counterproductive. It will actually reduce your generalization, meaning that your training error will look great, but your test error will look terrible. Also, when you have overlapping distributions, sometimes it makes sense to try to estimate posterior probabilities rather than trying to refine the tree down to purity. And when you're estimating posterior probabilities, you need more than one point in your box, basically. So by the way, one way to think about this is to compare it with the nearest neighbor algorithm. At the very beginning of the semester, I showed you the difference between one nearest neighbor and k nearest neighbor. And you might remember that one nearest neighbor gives you these very jaggy boundaries when you have stuff like overlapping distributions, and it's not very reliable. By using k nearest neighbors, like maybe 15 nearest neighbors, you get smoother boundaries that look more plausible for some data sets. Well, with decision trees, when you refine a decision tree all the way down to purity so that every leaf node has only one class, that's a lot like one nearest neighbor. And when you maybe refine it until there are 10 nodes in every leaf and stop there, regardless of the purity of the leaves, that's more like 10 nearest neighbors. Well, it's not, the number changes, but the analogy is there. If one nearest neighbor overfits, then a pure decision tree will probably overfit too. Let me give you a little figure that hopefully will clarify what I mean by estimating posterior probabilities. So imagine in the middle here is a decision tree. This decision tree only has 3 leaves, but that's okay. And we have points of 4 different classes there: yellow, red, green, black. And so instead, there's 2 ways you could approach this box on the left, for instance. This leaf node here. One way is I could say, well, the yellows win. The yellows outvote all the other classes, so I'm going to give that box a yellow label. That's one thing you could do. But the second thing you could do is instead you could actually output posterior probabilities for each class. In this case, we just estimate the posterior probability is the number of yellow points in the box divided by the total number of points in the box. So, there's 20 points in that box, 13 of them are yellow, so my posterior probability for class yellow is 13 out of 20. For green is 4 out of 20, for red is 1 out of 20, for black is 2 out of 20. So just reading what's in the box, really. And likewise, this box here has a different set of posterior probabilities. All right, so if we're going to do this, if we're going to stop early, then we need to think about what we return, what we reach a label, when we reach a leaf, like you have a test point, you walk down the tree with that test point, you reach a leaf, now you want to know what label do I return? How do I classify this point? Well, that leaf might contain multiple points, and they might not all be of the same class. And so what do we return? Well, it depends on whether you're doing classification or regression. If you're doing classification, then you've got essentially two choices. One is you could do a majority vote, or if you have more than two classes, call that a plurality vote. Or you could explicitly return posterior probabilities for each class. Which effectively means you return these numbers here. So that's what we do when we're doing classification. If we're doing regression, probably we're going to take the mean or the median of the labels of the points. So that's what we're going to do when we reach a leaf node. With that in mind, let's go back and ask ourselves the question, how do we know when to stop early? What should our criteria be for not splitting a node even though it has more than one class in it? Well, there are a whole bunch of stopping conditions you could apply. Which stopping conditions you apply are really going to depend a lot on your application. You have to understand your application and what's reasonable and what's not reasonable for how you think the points are distributed. But let's give some examples of ideas you could use for when not to split a node. One thing you can do is you can actually measure how much your cost function is improved by a split. So if your weighted average entropy, or for regression, your weighted average error doesn't go down enough, then you could say, okay, I'm going to stop here. There's no point in doing this split because I don't think the children are doing a better job than the parent is already doing. I got to warn you, though, that this is a dangerous stopping condition. And the reason why is that in decision trees, it's very, very common that you get a situation where you do a split and it seems like you've got virtually no information gain. The split doesn't seem to be making much progress, but the next split, lower down in the tree on the next level, makes a lot of progress. So you think you're not making progress, you think you're not making progress, and then suddenly you're making a lot of progress. That happens. And that is why, although you could use this as your stopping condition, it's usually better to do something else that I'll talk about in a few minutes called pruning. So I'll get back to pruning soon, but let's finish this section first. Let's look at what other stopping conditions you might use. So one natural one is maybe you don't require, you just have something that's almost pure, like, maybe 95% of the points in the tree node have the same class. That's good enough. And this makes a lot of sense if you think you have some outliers, points that are just have the wrong label. You don't want an outlier to force split a node that ideally would be pure already. And also if you have overlapping distributions, well, once you reach the point where you're 95% class C, that's probably good enough. You know, that's probably the best you can hope for. Now, one stopping condition that might data is to stop when a node just contains few sample points. You know, maybe you say, once a tree node has 10 or fewer sample points, I'm not going to refine it anymore. So that's one way to handle really large data sets, but probably a better way is to look at the size of the cell itself. Specifically the length of the longest edge of your rectangular prism. So if the cell, the rectangular prism represented by the current tree node, has edges that are all tiny, you might know that you are working in a domain where below a certain resolution there's no accuracy anyway, so it makes no sense to refine below what you believe your method or your measurements can resolve. So you're not going to keep cutting up the tree nodes smaller and smaller when they're already below what you believe is the resolution of your method. That makes no sense. And so that's probably a more effective way to deal with big data. If you have 1 billion points, but you only want to have 1 million nodes in your tree, set a threshold on the shortest edge length. Another thing you could do is you could just impose a direct constraint on the depth of your tree. So once you reach tree nodes at a depth of 20, you just say, I'm not going to refine beyond that. But this is kind of a dangerous stopping condition. You might just get a bad decision tree with poor predictive power if you do that. And lastly, I've always say that validation is the answer to everything. This is no exception. When you're trying to decide whether different ways of configuring your tree are good or bad, you can use validation. You can take your validation points and see how well each different variation on your tree predicts the classes of those validation points. Now, validation is kind of expensive, right? You have to take all your validation points and put them in the tree and figure out where they go and figure out the validation error. But if your goal is to avoid overfitting, it's a good idea. But it's more effective to grow the tree a little bit too large and then use validation to prune it back. So that'll be my next topic, is pruning. Any questions about stopping early before I talk about pruning? Yeah. So in this comment here, I've been asked to clarify what an edge is. And so coming back to our figure here, actually, maybe I like this figure better. An edge of the cell, this is an edge of the cell. This is an edge of a cell. So with each cell, you look at all of its edges in every feature dimension and look at which one's the longest one. And then if they're all short, like cell R5 here, its edges are all relatively short. Maybe I say, that's small enough, I don't need to split that anymore. But if I look at R3, well, it does have a short edge, but it also has a really long edge. And so who knows, maybe the points here are totally different than the points down here. So since it has one long edge, maybe I should split it. Other questions? The idea that we're going to talk about next, which is very closely related to the previous idea, is the idea of pruning. And here what you do is you start by growing your decision tree too large, so it's too pure, and then we trim it back. And we're going to use validation to make decisions about which leaves to prune from the bottom of our tree. Specifically, we're going to check if I remove these two leaf nodes from the bottom of the tree, does my validation accuracy get worse? If it doesn't, might as well prune. If it gets better, really should prune. Now, this has been empirically found to be a lot more reliable than stopping early. Over-refining, pruning it back is more likely to give you good validation performance, good test accuracy than stopping early is. All right, so a couple of things I just want to illustrate. Suppose this is your decision tree. Here's some splits. So when I talk about pruning, what pruning effectively means is I take two siblings, both of whom have no children, and I get rid of them, remove them from the tree. That's pruning. I'm not allowed to prune a node that has children. But if I make the decision to prune these two, then now this one has no children. And then I might decide that I want to prune that one and its sibling too. So pruning kind of recursively works from the bottom of the tree up. If I decide that I don't want to prune those two nodes at the bottom, if I decide that that's a good split, I like this split a lot, then I cannot prune this node, and I don't even think about pruning that node. I don't even consider it. So, which means that this node will stay. So that's the first thing I want to clarify. The second thing is, you might think that validation is very expensive. You know, here I am, I've got this tree, I need to take all my validation points, figure out what leaf each validation point is going to go to. So maybe these are my validation points. And then, after scoring the accuracy of this decision tree, now every time I think about pruning, well, now I have to do it all over again, right? I have to once again compute the validation accuracy of my validation set on this tree. But you'll notice that there's a clever way that we can speed it up. Basically, you take all the points in that node and all the points in that node, and they're going to be in this node if we prune those bottom two nodes, right? So I can, if I know the validation accuracy on the original tree, I can very quickly compute the validation accuracy on the pruned tree by just adjusting So no longer do I take into account the validation error in these nodes, scratch that out, but then add in the validation error for that node. And so you really just compare the validation accuracy in those three nodes. That's all you need to do to decide whether to prune those nodes. For this to work out, for this to be fast, what you need is a data structure that stores, for every leaf node, a list of all of the validation points that wind up in that leaf node. And so once you have that list, you can compute the validation accuracy changes of any pruning operation very quickly. Lastly, I want to repeat that the reason why pruning often is a lot better than stopping early is because it's very common to have a split where the information gain is very small, followed by a split where the information gain is much larger. And if you stop early, you will never find out that the second split would have been a good one. If you say, okay, information gain 0, I'm going to stop here and not even build those nodes, you'll never find out that at the next level you would have had a really good information gain. If you build the whole tree and then prune back, you can see that information gain and say, oh, I don't want to prune that. Your textbook, Introduction to Statistical Learning, gives an example showing the effectiveness of pruning in a particular case. What they use as data, so the data's on the right, look at the right graph first. What they're trying to do is take baseball hitters and predict their salaries. And they have two features based on which they can do this prediction. The horizontal axis here is the number of years that the player has been playing Major League Baseball. The vertical axis is the number of hits, or the proportion of hits per 1,000, I think, for each player. And so each little brown point there is one player, categorized by these two things. And so then what they did is they built a decision tree to try to predict the salary of these players. So we're doing a regression here, not classification. And on the left, what we see is, well, we build a decision tree with 10 nodes, and then we start pruning it back. So what we're seeing is various prunings of the same 10-node decision tree. And the horizontal axis here is the tree size. So this 10 here is the original full tree that we build. And then we prune it back to smaller numbers of nodes between 1 and 10. And the cross-validation results are the green line, which is sort of at the top here. And if you look at that green line, you'll notice that it's smallest with a tree size of 3. So cross-validation says prune back the tree until it's only 3 nodes. And that's what they did. And this is not uncommon because things like this salaries are hard to predict. So this particular regression says if you're in this box R1 on the left, then your expected salary is $165,174. And if you're in this box R2 at bottom right, then your expected salary is $402,834. And if you're in this box here, R3, then your expected salary is $845,000. So the best predictor is, are you a rookie or have you been around for more than 4.5 years? If you have been around a while, then your hitting performance starts to matter. If you're a rookie, then the hitting performance is not yet predictive. Any questions about that? Yeah. Mm-hmm. Mm-hmm. I think decision trees tend to work pretty well with high-dimensional data. They often ignore many of the features because the less predictive features kind of get sidelined for the more predictive features. When you mentioned k-means, which is a fundamentally different thing. K-means is a clustering algorithm. So, oh, k nearest neighbors. Okay. So, do you still have a question left? I'm not sure what you're asking now. Oh, yeah, I think decision trees can work very well for high-dimensional data, absolutely. But just keep in mind that they do tend to ignore a lot of the features altogether, which often is a good thing, but occasionally might not be. Mm-hmm. What are we looking for in the graph on the left? Well, the cross-validation accuracy. So the green line is the cross-validation, well, error, actually. The vertical axis is the error when we do cross-validation. No. I mean, there's three different point sets here. There's the training set, the validation set, and there's also a test set. And they've graphed, so the three lines, the three colors on the left, correspond to those three sets. You can see the training says that the tree keeps getting better and better as we add more and more nodes, but the cross-validation does not agree with that, and neither does the test set. Question there? How do we interpret the test set curve? Not sure what you mean by interpret. I mean, I will say that the test set curve says that maybe we should have actually stuck with the 10-node tree. There's a difference between what the cross-validation curve is telling us and what the test curve is telling us. I don't know why that happened in this particular data set, but it does happen. Sometimes your validation data is not a good representative of your actual test data. So, but every machine learning algorithm has that flaw, not just this one. Yeah? Mm-hmm. Uh-huh. Well, I mean, it's true that maybe instead of splitting over here, you should have split over there. We do not, so finding the optimal tree is clearly an NP-hard problem. So we cannot, we're not going to get the optimal tree most times in any really complicated problem. All of this, the cost functions we use are just heuristics. The methods of stopping early or of pruning back are just heuristics. And like any heuristics, they're limited. They don't always give you the optimal solution, or sometimes they don't even give you one that's close to optimal. But these tend to work well in practice, and so they're used a lot. Yeah, so you can prune some branches and not others. I think in this example, the test set was so small that, the tree was so small that there was really only one direction to prune. So our next big topic is somewhat related and somewhat not. Ensemble learning is a general technique of combining a bunch of different machine learning algorithms, a bunch of different classifiers or a bunch of different regression schemes, usually classifiers, to compute an answer collectively. It's most commonly used with decision trees, but it doesn't have to be. Decision trees definitely provide a good motivation for it, though. So let me tell you the advantages of decision trees as we've learned them so far. They're among the fastest classifiers. They are certainly in some ways the simplest classifiers. They often give you interpretable results that are easy to explain even to your grandmother. They are, moreover, invariant under scaling. So if you take one of your features and divide it by 1,000,000 and rerun with the new data, you get essentially the same decision tree. And they're invariant under translation, too. It doesn't matter where the origin is of your coordinate system. You get the same result. And they also tend to be robust to irrelevant features because they just choose not to split on features that have no predictive power. But they're not really the best at prediction compared to other methods we've studied in this course. So that's their biggest flaw. And part of the reason for this is that they, in terms of the bias variance trade-off, they tend to have high variance. On the right side, we can achieve very low bias. It's a very nonlinear method with very nonlinear decision boundaries. We can refine it as tightly as we want, and thereby get the bias down. You can get usually zero training error if you want it, but you pay for that with variance. So what do I mean by that? One example is, suppose that I have a training data set. I split it into two halves, and I build a decision tree on the one half, and I build a decision tree on the other half. It is not uncommon for those two trees to turn out very, very different. In particular, if each of the two trees pick a different split at the root, then you're going to wind up with possibly very different decisions all the way down. So that's one reason why decision trees often have high variance. So we want to think, is there a way we can fix this? Well, one analogy to that is, imagine that you have a random distribution of real numbers, and you are choosing numbers from that distribution. And what you want to know is, what is the mean of the distribution? Well, we all learned in statistics class that what you do is you sample a lot of points from that distribution. You take the sample mean, and that's an approximation of the mean of the distribution. And if we choose lots and lots and lots of these random points, we get a better estimate of the true mean. So you might ask yourself, can you reduce the variance of decision trees by taking the average of a bunch of different decision trees? Well, yes, you can. One thing that's interesting is that this idea might work with human beings as well. There's an author named James Surowiecki who wrote this book called The Wisdom of Crowds, which essentially is about how getting a large number of people together under the right circumstances to collectively figure something out can often lead to better results than one person alone. And so the sort of birthing story of this idea comes from a 1906 county fair in Plymouth, England, where they had a contest where contestants had to guess the weight of an ox. That's not an ox, by the way, but it's close enough. We'll get, that's a cow, but we'll get to the cow. But pretend it's an ox for a moment. They had a raffle where people guessed the weight of the ox, and whoever gets closest won a prize. Well, there was a scientist there named Francis Galton, and he did an experiment, which is he collated all the guesses and calculated the median guess. And the median guess was 1,207 pounds, and the true weight was 1,198 pounds. So the error of the median was less than 1%. Even the cattle experts who were present at the fair didn't estimate it that accurately. So, where this photo comes from is that in 2015, National Public Radio decided to try to repeat that experiment with this cow named Penelope. This time it was online, but they put this photo up and asked people to guess the weight of Penelope. And they got 17,000 guesses, and the average guess was 1,287 pounds. And Penelope actually weighed 1,355 pounds, so the crowd got it right to within 5%. Not quite as good as the fair, but they didn't get to touch the cow either, so maybe that's why. So anyway, the main idea here is that sometimes the average guess of a lot of average people, lay people, might be better than the guess of an expert. And so it is with learning algorithms. We talk sometimes in machine learning about a weak learner. Essentially, a machine learning algorithm is a weak learner if it does better than guessing randomly. And if we combine a bunch of weak learners together, we can get a strong learner, as long as those weak learners are independently stupid, meaning that all of them guess better than chance, maybe just a little bit better than chance, but they all guess wrongly in different ways. So the ways in which they are wrong, if not correlated, then we can take the signal, the ability of these people to guess slightly better than random, and combine a bunch of them to get a signal that's much better than random. And there are many ways that we do this in machine learning. But they all involve taking an average, so to speak. I'll talk about what I mean by average soon. But first, the average of what? The output of, well, we could use different learning algorithms. The idea being that, maybe decision trees and SVMs each have different strengths, and if we combine their outputs, maybe we'll get something better than the sum of the parts. Or, more commonly, it's a lot of work to write a bunch of different learning algorithms, so an easier thing to do is run the same learning algorithm on many different training sets. So if we have a lot of data, this is great. Make a bunch of different training sets and run the same learning algorithm on all of them, but often we do not have a lot of data. Is there something we can do with this idea if we have only a small amount of training data? Well, people have spent a lot of time thinking about that, and a couple of solutions that are now very well known are called bagging and random forests. So bagging, the idea is that you run the same learning algorithm multiple times. The problem is you don't have enough data to make a bunch of different independent training sets. So what we do instead is we take our small training set and we take a bunch of random subsamples of that training set. I'll talk more soon about how to do that. And then there's some people who say, okay, that's great, but it's not random enough. So thus was motivated another algorithm called random forests. Random forests is bagging on decision trees, plus you inject extra randomness into the choices of what splits you make when you build the decision tree. So these are decision trees where we inject some randomization so that each decision tree will be different, but hopefully still good. And you apply each of these decision trees to a random subsample. So we're still doing bagging, but we're adding more randomness on top of bagging. And so again, the last two are the ones we use if we just don't have enough fresh training data for every learner. So although averaging is not specific to decision trees, it can be used with many different learning algorithms. It works particularly well with decision trees, and it's very popular there. And so now let me just address, what do I mean by the average of the output? Well, that depends on whether you're doing regression or classification. If you're doing regression, then you literally just take the average of the outputs of all your different regression algorithms. And by average, sometimes the median makes sense. That's what Galton used. Sometimes the mean might make sense, although that is more vulnerable to having one of your regression algorithms being really bad and giving you a comically large number. So maybe the median is more reliable in a lot of cases. If you're doing classification algorithms, well, it's a little less clear what average means, but we just do kind of the obvious thing. You take a majority vote. So if you're just trying to decide whether a test point is in class C or not, well, you just throw your test point at 9 different classification algorithms. You get back 9 votes saying this is in class C or this is not in class C, and the majority wins. Or if you are using algorithms that actually compute an estimate of the posterior probability of any particular class being the correct choice, you could take the average of those posterior probabilities. Again, your choice between the median or the mean. So when I talk about taking the average of a bunch of posterior probabilities, I want to show you a little visualization of that, because I think that this is really interesting what that can actually look like. So I'm going to show you a quick little video here, 10-second video. And what we're going to see is on the left, we are going to generate a bunch of different decision trees that separate the yellow points at upper left from the red points at lower right. As we generate all those decision trees, you'll see them all one by one on the left. And this decision tree, by the way, is called a stump because it only has depth 1. We choose one line to separate those points. On the right, what you're going to see is the average of all the decision trees that we have visualized on the left. So let's watch that. All right, so on the left, we flashed a bunch of different decision trees at you. You'll notice that on the right, when we take the average of the values output by those, we've essentially regressed the posterior probabilities. So this is telling us that in this yellow region up here, it's extremely likely that any test point is in class yellow. In this region down here, it's extremely likely that any test point is in class red. But you can also see there's this orange region here where the posterior probabilities have naturally come out to be about 50%, because half the time they were yellow on the left-hand side and half the time they were red. So you can really think of this as a estimate of posterior probabilities. That's the point I want to make here. And let me show you one more example. Now, instead of depth 1 trees, we'll use depth 2 trees. So we're getting really sophisticated. But we've got 4 different classes here. So again, we generated a bunch of different decision trees that separate these 4 classes. And on the right here, you'll see the posterior probabilities. And what you'll see is here's a band where it's not yellow, not green, but somewhere in between. Here's a band where it's not yellow, not blue, but somewhere in between. You might question if that's really the best graph of posterior probabilities. I'll show you some other choices that for this same point set later. But coming back to averaging, one of the most famous examples of averaging in action was the Netflix prize. So there used to be an open competition for the best collaborative filtering algorithm to predict people's ratings on films, and sponsored by Netflix. So the idea is you know people's ratings on previous films that they've watched. You want to predict what their future ratings will be on other films that they haven't watched. And the way you predict that is by correlating their tastes with other people who have similar tastes. So that's what collaborative filtering does, is it tries to figure out what movies you should watch, or what you should buy on Amazon, et cetera, et cetera. So the Netflix prize was a contest that ran for 3 years. Netflix provided anonymized data. The contest ended in 2009, but the winners at the time used an extreme ensemble method that took an average of many different learning algorithms. In fact, a couple of the top teams on the leaderboard decided to combine into a single team so that they could average their methods. Basically, they said, let's average our models and split the money, and that's what they did. So when you're doing averaging, here's a few things to keep in mind. First, it's usually an idea to use learners with low bias. And the reason why is because what averaging does most effectively is it reduces the variance. What it sometimes does, but not reliably, is reduce the bias. But you can't really count on it to reduce the bias. So if you want low bias, you should start with low bias and then use averaging to reduce the variance. So what that means is that when you're averaging decision trees, often it makes sense to make those decision trees relatively deep. Remember, the deeper a decision tree is, the less bias, but the more variance. Now, if you have learners that have high variance, which means they tend to overfit a little bit, that's okay, because the whole point is that averaging reduces the variance. Because each learner may overfit, but ideally each overfits in its own unique way. All right, so there are times when averaging reduces the bias because it increases flexibility. For instance, the average of a bunch of linear classifiers is not necessarily linear. You have a little bit more flexibility than linear. But this is not reliable. I mean, what averaging is reliable at is reducing variance. It's not so reliable at reducing bias. But an example of how it can sometimes reduce bias, again, is that if you have linear classifiers, averaging them will give you a decision boundary that's not quite linear. It's not perfectly flexible either, but it's more general than linear. Now, a side issue that comes up when you're doing averaging is the hyperparameter settings. Remember that when these algorithms, like SVMs, have hyperparameters, it often allows you to choose a spot on the curve between underfitting and overfitting, between bias and variance. Well, remember that I'm saying now that we want low bias. If we're going to do averaging, we can tolerate some extra variance to get the bias lower. So that means that the hyperparameter settings that you would choose for an ensemble of SVMs is probably not going to be the same as the hyperparameter settings you would prefer for a single SVM. So, in other words, the hyperparameter settings are usually different than what you would use for just one learner. Because averaging learners reduces their variance, but rarely reduces bias as much as it reduces the variance. Also, let me point out that the number of trees is kind of a hyperparameter. I mean, more trees will give you less variance, but I don't really want you to think of this hyperparameter as moving along the bias versus variance curve. The real curve here is variance versus running time. The more trees you add, the slower your ensemble method is going to be. So you pay with time to reduce the variance. Any questions about that? Yeah. Well, flexibility is another way of saying how constrained you are. You know, a linear classifier, for instance, is not very flexible. If you have a quadratic classifier, like you use quadratic features, now you can use curves instead of straight lines to cut up your data. That's more flexible. So that's what I mean by flexibility. The official word is capacity, but since I haven't introduced that word, I figure it's even less intuitive at this point. But for those of you who have heard the word capacity, that's what I mean by flexibility, is the capacity of your learning method. All right, so I want to go into more detail about a couple of these methods. One of them I mentioned briefly is bagging, and bagging is actually an acronym. It's short for bootstrap aggregating, so to speak. I am pleased to say that this was invented here at Berkeley by Leo Breiman in 1994. Leo Breiman was a statistics professor right here at UC Berkeley. And interestingly, he did his best work after he retired in 1993. The very next year, he published the bagging algorithm. And then from after that, he went on to co-invent random forests as well. Unfortunately, he's no longer with us. He died in 2005. But his contributions are still remembered. So bagging is a randomized method for creating different learners, many different learners from the same, perhaps small data set. And you can use it with all kinds of learning algorithms. It's definitely not specific to decision trees. Yeah, it works for many different algorithms. But one exception I should mention seems to be k-nearest neighbors. I'm not sure why, but bagging seems to mildly degrade the performance of nearest neighbor algorithms. So the idea is, suppose you are given an endpoint training sample. Then what we're going to do is we're going to generate a random subsample of size n prime by sampling with replacement. And I've got to emphasize that part, sampling with replacement, which is weird. Yet it works well in this case. And so what that means is that when we take a subsample of our training data, some points will be chosen multiple times because we're sampling with replacement. And some points won't be chosen at all. So, simple example. Consider a one-dimensional feature space. So each of our training points is just a number. Let's suppose our training set has just these 6 points. That's it. Well, all right, let's take a subsample. I'm going to randomly choose a point, 6. I'm going to randomly choose another point, 3. Randomly choose another point, 6. Wait, I already chose 6. We're sampling with replacement. That's okay. 1, 9. Let's do it again and get a second subsample. So here's subsample number 2. Randomly choose 8, then 8, 4, 9, 1, 8. So I wound up choosing 8 3 times. Well, I can do that. All right, so one thing that's interesting is that if the subsamples are the same size as the original sample, as I expressed here, and n is relatively large, then on average an expected 63.2% of the points are chosen, approximately. So less than 2/3. Again, this fraction itself varies randomly. So we take each subsample, like we take this subsample and we build a learner on it. We take this subsample and we build a different learner on it. When you are building a learner, it's natural to ask, what should I do with a point that has been chosen 2 or 3 or 4 times? All right, well, let's suppose you have a point that was chosen j times, and so is repeated j times in the subsample. Essentially, you treat it as a point that has a greater weight in the learning algorithm. And what exactly that means is going to vary from learning algorithm to learning algorithm. But the intuition is, if I have chosen the same point j times, I want to treat it exactly the same way I would treat j different points that all happen to be bunched up infinitesimally close to each other. And so, to give 3 examples of what that means, if we are working with decision trees, then a point that was chosen j times for the subsample will have a j times bigger contribution to the entropy term. So you treat it as if it's 3 points of that class rather than 1 point of that class. If you're doing support vector machines, then a point chosen j times will mainly affect the penalty term that we are optimizing. So it will have j times as big a penalty if it violates the margin. Its slack is penalized j times as much as a point that's only chosen once. If we're doing regression, Well, we're doing an average of cost functions, so you just repeat the cost function for that point j times. In other words, that point is going to incur j times as big a loss. So just multiply its loss by j. All right, so, oh, question? Yeah. Well, it's up to you. I mean, if you've written your, you've probably written your classification algorithm in such a way that if you just feed in the same point j times, it will do the right thing. That's usually how it works out. You could explicitly code this if you want, but usually you don't need to. All right, so let's say that T, capital T, is the number of learners. T stands for trees, by the way. Again, bagging isn't always used with trees, but that's the most common application. Once you have trained your T weak learners, then you build on top of them a meta-learner. And so the meta-learner is just a very simple piece of code that takes in a test point. You want to classify it or regress it. And then it returns the average output or the majority output of those learners. And that's pretty much all there is to it, other than to say that it often works well. Any questions about bagging? Yeah.
You mentioned that each of the learners has to operate independently. However, it seems that the subsamples can overlap, that there are elements in both subsamples. So in what sense do they have to be independent?
In what sense do they have to be independent, like the different learners? Well, obviously they're not completely independent. No, they are correlated because they have correlated training data here. Nevertheless, there is some variance between them that we can exploit because each decision tree is making different decisions about where to split. And in practice, I mean, this is very much a practical observation. This often works very well and reduces your variance and gives you better generalization, even though the trees are not truly independent of each other.
So you don't have to like partition the data first before making the subsamples?
No. No, all the subsamples come from the same data. A related idea on top of bagging is called random forests. And this is based on the idea that, okay, bagging works all right, but maybe that's not random enough for me. I want even more randomness. Why? Why am I saying that? Well, with decision trees, or sorry, with bagging, the decision trees often look very similar to each other. And not always, but sometimes they do. And one reason why you see this phenomenon is suppose that there is one really strong predictor in the data. Often you will wind up seeing the same feature split at the top of every tree. Like, for instance, if you're building decision trees to identify spam, you might find that maybe the root node of every one of your trees is Viagra, or at least every one of the trees that got Viagra is one of the subsamples when you did the bagging. The idea here is that when we are averaging trees, we're reducing the variance. But if those trees are too strongly correlated with each other, then then we actually aren't reducing the variance much at all. We are introducing bias. So the idea is let's introduce even more randomness into the tree building stage so that we don't always get Viagra as the root node. So the main idea here is that at each tree node, as you are building the decision tree, you're not going to consider all of the features. Instead, you're going to randomly choose M of the D features. And then you try each of those splits. You only try splitting on those M features. Instead of trying to split on all D features, you just try to split on the M that you have randomly chosen, and you see what is the best split from among those M features. You are not allowed to split on the other D minus M features. And note that it's very important we are going to use a different random sample of M features at every tree node of every tree. No two tree nodes in the same tree or in two different trees necessarily have the same random choice of features. How big should M be? Empirically, it's different for classification and regression. As a rough rule of thumb, people have found that taking the square root of that true number of features is a good subsample size if you're doing classification. But if you're doing a regression, you actually want to choose a bigger subsample, about a third of the features. So if you have a 100-dimensional feature space, you randomly choose 10 of those features and pick the one of those 10 that gives the best split. Having said that, M is a hyperparameter, and you could try tuning it with validation as well. Now, if you choose M smaller, then you get more randomness in your trees.